Welcome to the fundamentals and all the other fun fan stuff that Greg's going to talk about today. If you have any questions, just a reminder, put them in the chat, and I'll be monitoring that, and I'll grab those and bring them up as appropriate, and funnel those to Greg. And I think Greg's itching to get started, so I'll let him take it from here.
Awesome. Well, I'll do a quick share. Everybody can see what we're looking at?
I've got it.
Awesome. Well, quick introduction here. My name is Greg Allen. I'm an application engineer within the Power Roof Ventilators business unit of Greenheck. Been with Greenheck for 9 years. I do a lot of work with motor and control technologies, as well as fans and education. So this is kind of right up my alley. Thank you, Dorsey, for bringing me in, give me opportunity to kind of present one of the topics that's really near and dear to my heart. The way it was kind of sent to me was, a fan fundamentals with a emphasis on good fan selection and efficient fan selection. So I'm going to kind of sprinkle in a lot of commentary as we go through some of these slides. Please feel free to send in those chat questions. We'll try to keep some time for the end. And with that, I guess we'll get rolling here. All right. You can't start off with fundamentals without starting off with the fan laws, also known as the affinity laws. And there's 3 affinity laws that we're going to talk about. The first fan law on the screen, what this is showing you is that there's a relationship between any change in RPM and what'll change for the CFM. And this is showing us that it's a 1-to-1 change. So 10% more CFM is gotten by a 10% RPM increase, right? So I call this the good fan law. This is one that makes everybody happy. You come to T&B or test and balance, and you're 5% short on air, 10% short on air. This is a nice little fan law for you. Now, something to keep in mind, the fan laws really are rooted in you have a known point you're starting from, RPM base, CFM base. You have these known points, and you have not changed the system. You haven't added more ductwork, changed dampers, etc. So if you haven't changed anything in your system, you can now really see where you're going. So that's kind of one of the biggest values of the fan laws. So we got the first fan law. Pardon. Second fan law that comes in, I call this one the uncomfortable fan law. And it's really what it's doing is it's saying that as RPM changes, your static pressure in the system is going to change by the square, right? And that's why I call this the uncomfortable fan law, because, 10% more air, now I'm fighting against, 21% more static pressure, right? So we're talking higher sound, and leads us right into the third fan law, which I call the expensive fan law. And that is telling us is as you change RPM, the brake horsepower needed will change by the cube, right? So if a simple 10% more CFM is going to require 33% more horsepower. Now, a quick terminology 101. The difference between horsepower and brake horsepower. Whenever you see just straight HP, and we're not talking Hewlett Packard, whenever you see horsepower, we're referring to the nameplate of the motor, right? I have a 5 horsepower motor, right? It's right on the nameplate. When you see BHP or brake horsepower, that is the horsepower consumed at the point of operation. So if I have a fan that's got a 5 horsepower motor, and it currently is, brake horsepower at 3.2. Great. I've got more horsepower than I need, which is much better than the other way around. If you have a 5 horsepower brake and a 3 horsepower motor, that's not going to work too well, right? So really the fan laws are a great place to start, foundational, make sure we're all on the same page. So we'll move into kind of that next section here. Oop. All right, there we go. Sorry, I had a little miscommunication with the keyboard. So now that we have the fan laws, I kind of want to bring that. The fan laws are like some of the math behind fan curves. And to me, fan curves are an amazing study. They're alive, right? There's so much information. There's the basic base, what everybody gets from it, and then there's more. So we're going to try to use this class here to shed on more, right? But as I'm looking at, a fan curve, and I just took a snapshot, common fan curve here. Let's define what's on the screen. First thing is across the x-axis, the horizontal, that's our volumetric flow, right? Cubic feet per minute. That's how much air we're going to move. On the primary axis for y is our system resistance, right? This is the amount I am fighting against, or I'm trying to overcome that pressure. And lastly, on the other side, we have a secondary axis, and that's got our brake horsepower scale. So right off the bat, there's our axes. Now let's kind of get into the meat and potatoes. The red line or the red curve on the screen, right? This is known as the fan curve, right? And the fan curve, this is rooted in test data, right? We took this fan, we put it in an AMCA test chamber and took all the values and found the relationship between static pressure and CFM, right? And it makes sense. The lower the static pressure is, the higher the airflow. As static pressure goes up, airflow is going to drop, right? So the shape of that red curve makes sense. And this is represented from data at a specific RPM, right? Now, another thing you can see right on the screen, I wrote 1448 fan RPM, FRPM. Terminology again. RPM is typically what the motor is turning. When you see fan RPM, that's what the impeller is turning, right? So anytime you see FRPM, if it's a direct drive, that is the same RPM as the motor. If it's a belt drive, that is showing you your relationship through the pulleys and shivs between the motor and the belt. All right, so we have a fan curve, which is that red line, our fan RPM, but we also have this blue kind of a squared looking parabola, right? And this is a system curve. This represents all the duct work, the 300 feet, the 6 elbows, the reduction, all that has been added up, right? How much system resistance is going to be added to the system to overcome in this entire system, right? And that is represented by that curve. Now, the neat part is where they intersect, the system resistance curve and the fan curve. That is called the operating point. So whatever fan we're looking at this RPM, at this static pressure, will move this amount of air, right? And how we read this, we got one more curve, the brake horsepower curve. And brake horsepower is really recorded as we're testing to find our CFM static pressure relationship. We're also taking data points. So how much horsepower did it take at that point to move that air? Now, a brake horsepower curve, that's the black dashed, that can be above the operating point, below the operating point. It actually has no correlation to the fan or if it's a good or bad selection. It's just depends on the scale to the right-hand side, right? And when you read the brake horsepower curve, the key is that you go from the operating point and you draw a line up or down until you hit the brake horsepower curve, and then follow it across that secondary axis, right? So in this scenario, we're, to move 1200 CFM against 2 inches of static pressure, That's our operating point. It would require 0.85 brake horsepower to do this, right? So you can assume we're going to have at least a 1 horsepower motor in this application. Now, there is a little bit more information on the screen that we want to point out, and that's that shaded area. This is the do not operate zone, the surge zone. This is an area that a fan can operate in, but it's not recommended. Most manufacturers will give you this area that says, do not pick a fan operating in this area. Kind of circle it here for you. Now, kind of zoom in a bit. Let's look at one of the scenarios. In this area, things like, stall or surge or hunting can happen, right? These are going to affect the performance and possibly even the life of the fan if it's operated in this area. But let's look at a specific scenario. If I draw a line right here at just under 2.2 inches of static pressure, that pressure hits the fan curve in more than one place, right? So we're at 1100 CFM or 200 CFM. So which volume of air would this fan move if I actually have 2.2 inches of static pressure? Which one does it move, the 200 or the 2200, right? You don't know, I don't know, and the fan doesn't know, but it's going to try to do both. So what it'll do is it'll do what's called hunting. The fan will actually speed up, move the higher volume, and then do a quick unload and move the lower volume, and then it'll load back up to high and then drop to low. In this scenario, it's like taking a manual transmission car and going from fifth gear to second gear, fifth gear to second gear. That car would not last too long if you were to operate it that way. And hunting for a fan can be just as fatal. You'll have metal fatigue, your components wear out. Not to mention it'll be very annoying to listen to, and your airflow is all over the place, right? So this is just kind of an example of why you don't want to operate within that do not operate zone. All right, so I'll kind of back up here. This is your basic fan curves. This is what pretty much every manufacturer is going to try to get across as a bare minimum. How is this fan going to operate? At what RPM is it going to be operating? Where does it intersect your system resistance curve, your system curve, your brake horsepower? So this is kind of that key information that's being handed across. But there are some other fan curves, additional, that can provide more information. So here, this is just an RPM fan curve, right? One of the rules of how fan curves are made, and this makes sense if you go back to the fan laws. If you speed up or slow down a fan, you take the original fan curve and you just offset it parallel. It maintains the same shape. Now, where you interact with the system resistance curve changes, and you're going to have higher static pressure. You're going to have, higher CFM in that same point or lower. But this gives you an idea of, okay, what RPM do I need this fan to operate at? Say I have 2 points of operation, or I'm trying to extend the life of this fan into a secondary application, right? So this is where the value of a RPM change curve would be. I want to now that I kind of built, the base, I want to do a quick reality check with everybody. On the screen, I've got my fan curve, my system resistance curve, right? I got my interaction. So my question to you is what happens when you've added up all the ductwork? I needed 1200 CFM against 2 inches. That 2 inches represents all those elbows, the whole works. And then it's installed, and you go back to do a review, and your as-built, the ductwork is going around a couple of columns. That was not in your design, right? So what's going to happen? Static pressure is going to be a little different than you added because you didn't account for those extra elbows. So if I were to look at a fan curve, and this is where some of the life comes in, if I add static pressure, I change the system, and that curve starts arcing up. Right? Notice I'm hitting at a new point. This means that because of the extra static pressure, my CFM is going to change. And in this scenario, more static pressure, I'm going to have less flow. But in the end, I still need 1200. That's what the fan was ordered for. That's what the need is. So now I'm looking at a scenario where, because I have the more static pressure, I'm going to bump up the speed to get back to where that intersection between the two curves is on my 1200 CFM line, right? So in this scenario, I need to bump up to 1525 fan RPM to get back to what I needed originally. Now, if I have less static pressure than I thought I would need, right? I thought 2 inches, turns out it's a little less. As you have less, the system resistance curve will lay down. And of course, same scenario, I'm going to have to adjust the speed of the fan. And now I have to slow the fan down. So I'm only moving the 1200 CFM. So now I have a new operating point at 1365 fan RPM. So when you're looking at fan curves, just kind of keep in mind that the actual as-built static pressure, how that changes, can actually change the shape of that original fan curve that you were provided, right? This also kind of brings in, like I've done 2 RPM changes here, one up, one down. Something to think about is what technologies are out there that allow me the freedom to speed up or slow down. And right, comes to mind is like EC motors, especially if you're in the fractional or low nominal horsepowers. That's has built-in ability to give you a fairly large range of operation. I mean, usually they have about an 80% turn down. That's a huge range. Turn up, well, the amount you have to turn up goes back to your original or initial fan selection. Did you select the fan, a small guy, the most cost-effective one that's maxed out just to hit your point? Well, there is no turn up in that scenario. I have another slide here that's going to kind of hit that even a little harder. I do want to kind of point out a few more common fan curves. This is all about providing you information so you can make better selections. I mean, so you know what tools you have in that quiver. And this is one of my absolute favorite fan curves. It's just a min-max fan curve. It's a curve that shows me, well, the red line, that's how I selected this fan. It's got the blue system resistance line, all that's the same. But now I'm throwing in a green curve. That green curve represents the motor that's initially on this fan has the ability to get up to 1530 fan RPM. So that's how much I have to turn up. But I also have a top purple line. This one's designated 2166 fan RPM. That shows you or represents the fan's maximum condition. Like if you put the biggest motor that fan can handle, that's the construction limit of the whole works. I also kind of show a 483 fan RPM down at the bottom. And this is your typical turn down. It's either shown, like if it's an EC motor or has a VFD, it's going to show you like that 75, 80% turn down. Sometimes it'll show you like a 20 Hertz, wherever you feel your bottom is. This is kind of representing kind of a 20 Hertz turn down. So you can get a little lower than that yet on typical VFDs, but it's for kind of guidance to bracket what is my capability with the fan I've just picked. So I do not pick a variable speed fan without looking at this curve. Is there a question that you want me to hit before we move on?
Yeah, Greg, I think this is a great fan curve and slide to answer this question in the chat. Jake asks, the brake horsepower curve is only for the labeled RPM. Is that correct?
That is correct.
So you have 2 brake horsepower curves?
Yeah, for what's on the screen here, the 1 brake horsepower curve, the top one, I say BHP at max fan RPM. So that is associated with that 2166 fan RPM. The lower brake horsepower curve is then associated to the red as selected. So that's kind of what I'm showing on the screen. So in this scenario, I need 0.85 brake horsepower for what I needed at, that 1200 CFM. But I'm showing you that this fan with the biggest motor possible, I could actually hit about 1800 CFM at 4.5 inches of static pressure. But at that point, I would need, a 3 horsepower or maybe even a little bit better motor to get to that RPM. Great question. Any others, or should we keep going?
Yeah, ready to move on.
All right, moving on. Oh, so I've got my fan curve. Just kind of spell these out for you. My max fan as selected. That means, the initial, I'm assuming this had a 1 horsepower motor on it. That's where you ran out of 1 horsepower. I've got my minimum and I got my maximum fan construction curve. Like I said, this is a very valuable curve. There are programs out there like eCaps. You can get in, you can sign in as a guest. It's a free account. But when you go in there, you can pick a fan, look at the fan curve. It shows you the original fan curve, but there's a little drop down and you can change it to show the min max curve. And I highly recommend it. The other part here, from this curve, I have this presentation, I have more information available to me. So like as fan as selected was 1530 fan RPM max, right? Well, quick little math, 1448 divided by 1530 is 0.95. What that tells me is if I pick this fan without bumping up the motor size, I am knowingly picking a fan at 95% of its capability. That's awesome if you have need for a lot of turn down, or you want to keep the motor as small as possible. But it also tells me that I only have the ability to turn my fan up 5%. If you are less confident in this project that you're working with, is that a good fan selection? You may get on site and find that now I have to put a bigger motor in it because I had more static pressure, right? I only had 5% as ordered. Also, one thing that this fan curve kind of builds into me is, hey, this fan can accept larger motors, right? That purple line's pretty far away. I can get up to a 3 horsepower motor in this. This is good because if I did have a problem, I could bump up to a 2 horse or a 3 horse. Some of the fans you're looking at, that green line might be right on top of the purple line. And in that scenario, it's telling you this is the biggest motor that this fan can handle. And if you have a scenario where you're short on air and you want to speed up, you're probably looking at a fan replacement, not a motor or drive set replacement. So you can infer a lot of information off of these. Here's another curve for you, and it's just showing alternate selections. This is actually a representation of different model or different sizes within that family, right? So the red, let me see. We picked a 240 XP. Okay, so the red line represents the fan we've been looking at as an example, but there's also a smaller fan and a larger fan that can hit these same performance points, just have different shape curves, right? And this is good information to know because, am I picking a good fan? Here's the shape of the other curves, and you did this without selecting other fans. You were able to just compare. All right, so let's kind of, I brought up the topic of making a good fan selection. What other tools do we have to provide you to know if you're making a good fan selection? One of those is a static efficiency curve. That's that black dotted line, right? And this represents, any fan has a large range of operation of what it could, depending on static, depending on RPM. But that doesn't mean that any point of operation and within that fan's capability is an efficient point of operation, right? In this scenario, you can look at the peak. I'll try to use my cursor here. You can look at the peak of this static efficiency. And really what it's saying is like this point right here, if we were to cross that fan curve, we call that 1650 CFM. If you would cross at that point, that would be its most efficient point of operation, right? But really anywhere kind of in here, and I'm going to throw a circle on the screen, I believe. Yeah, this circled region represents operating this fan in its most efficient spot, right? Now, total efficiency, difference between a total efficiency and a static efficiency curve. If you got a rooftop unit, like a little downblast, you're going to be looking at the static efficiency because you really only have pressure on one side that you're overcoming. Total efficiency is more like your inline fans, right? Where you've got pressure before and after you need to overcome with that booster. Same information, read the same way. But that's the difference between total and static efficiency. In this scenario, the peak operation would be at 52%. And notice I put a tertiary scale now on the right-hand side that I can draw a line across to see where my peak efficiency is. And so for this fan, its best efficiency it's going to get is 52%. And then am I within so many points of peak from there? All right. So I threw a lot of different fan curves at you, kind of started bringing in good fan selection, but there's a little bit more information. And this is becoming more and more common, especially when you start looking at, Washington, California, right? This term of FEI or fan energy index is creeping in the next 4.5 years. The Department of Energy will require all of us to play this game. Fan energy index is a single value that represents, wire to air efficiency, right? It's a really good look at fans. And this is a value that I can present to you. And just looking at it, you can see, was this fan picked in its efficient zone of operation? Or was this fan picked in a inefficient place of operation? So quick little fan curve. I'm going to throw on here what we would call an FEI bubble. But right off the bat, I can show you on this fan curve that this selection that's circled here is going to be a lower efficient point of operation. And that was just derived from my static efficiency curves that we looked at already. I'm telling you, okay, down here, you're gonna have lower efficiency. Your fan's gonna be a louder fan, right? And then I've got this other area where, okay, this is where I'm in that high efficient, low sound, sweet spot of this fan. But I'm gonna overlay this red area. And this red area represents everywhere that this fan could operate where it has an FEI value of at least 1.0, right? So that outer edge would be 1.0. Everything within that red circle would be greater than 1, right? So this is like that peak operation. Now, kind of back to all that information, if we were to, change the RPM up and down, you can see where I'm getting in a narrower spot of peak operation or in a little bit wider spot. These are all values where this fan is a good choice. If you're outside of that, you're going to have an FEI lower than 1.0. And this is really rolling into a lot of the requirements, the regulation, where an average good fan would have an FEI value of 1.0. Now, kind of stretch just a little bit further. When you do employ technologies that give you variable speed, right? Whether it's a VFD, whether it's a EC motor, even a belt drive fan where I could look at adjusting shivs and pulleys, right? I have that ability to offset that fan curve different directions, or we looked at that fan RPM curve. What that shows me though is that I could actually slow a fan down and get into a more efficient point of operation, or I have so much room to speed the fan up and maintain that higher efficient range of operation. So if you can picture offsetting that curve parallel. All right, another view of a fan energy index. The green dashed line, this represents this fan that I picked as an example, its entire range of capability, right? It could move almost 4,200 CFM and up to about 4.8 inches of static pressure. This is all the different points it could operate. But in this fan, this one area represents everywhere where the fan energy index is greater than 1. Right. And we were using for our example, a 24-inch wheel belt driven fan as an example. And if you overlay that on here, it actually falls in to the good FEI bubble. And that's encouraging. You know, even for an example, we picked a good fan here for this operation. But this points, I mean, if our point of operation was out at say 3,000 CFM and 1 inch, this fan could physically do that. It's just not an efficient point of operation. Going to be louder. Also, you may not be able to get the benefits of having an FEI greater than 1, or meeting regulation that requires 1 horse and up, that you do have a minimum FEI of 1. In those scenarios, can I speed the fan up or slow it down to get back into a good zone? Can I go from a standard wheel to a partial width wheel? To all those things are going to tweak the shape and size of that fan energy index bubble. Also, you may want to just keep in mind that, like for the last 5 years, we've been picking this fan with a 16-inch wheel, right? It can move the air we needed. It was a perfect fan for that. It was very cost effective. Well, when the requirements come in for minimum efficiency, I might be looking at that same application, and I might have to bump that up to an 18 or a 20-inch wheel, because here's kind of an overarching, rule of thumb to hang on to. There's a small fan screaming, which is very cost effective, versus a large fan moving slow. It is the larger the fan moving slower is going to be quieter. It's going to be more efficient. Anything you want me to relay into this one?
I think that was great.
Okay. All right. FEI's impact. All right. So when I'm looking at fan energy index, incorporating into our design process, whether you're designing the building or even me as a manufacturer, there's really 3 areas that it's going to hit, and that's fan design, motor type, and fan size, right? And when we look at fan design, there are different types of impellers. There's the propeller, the centrifugal wheel, there's mixed flow. The different type of impellers are going to have different ranges of where they're more efficient, right? A propeller is much more efficient at moving high volumes of air against very low static pressures. A centrifugal wheel is going to be much better at higher static pressures but lower volumes. So if you're looking to get, that minimum 1.0 or 1.1, whatever is needed, looking at alternate fans may become part of your equation now, and doing a good comparison of where is that fan moving in an efficient point. But then there's motor technology as well. I have, in the single phase world, this is very evident, right? If I have a single phase AC induction motor, the motors are not very efficient just by design. All right. So in that realm, I'm showing on the screen an EC motor, or electronically commutated motor, which in single phase, I mean, that motor is sitting 85% efficient. I mean, it's an extremely efficient design. When you get up into the three-phase world, three-phase AC motors are much more efficient. Um, but there's also EC motors that are even more efficient yet up in that range. To give you an idea, like a 2-horse AC induction motor is going to usually be around 86.5% efficient, which is really good. An EC motor at 2-horse, you can get them upwards of 91% efficient, right? So your gains are smaller, but more impact the wallet more as far as savings, picking up that 5 or 10% on that end. Also under motor type, I kind of want to throw in VFDs with EC motors. VFDs, again, EC motors, VFDs allow you an easy way to change RPM. So you can take a bigger fan, slow it down, and get into that efficient spot. Also, if you're doing a variable volume design for your building, I can move 2 different points of air, 3 different points of air, occupied, unoccupied, normal, and alarm. I have that range of capability because of the motor technology. And then kind of that last point I made on the previous screen, right? Fan size is the next thing. Today I might use that smaller fan shown on the screen. Tomorrow, to hit higher FEIs that are required, one of the things I should be looking at is, okay, can I up the motor technology? Can I go from AC to EC? How much efficiency does that pick me up in that design? But you may also want to look at, okay, I need to bump this up to an 18 or a 20-inch wheel in order to get me to where I need to go efficiency-wise. So now that I kind of talked about impellers, let's look at a quick screen. First things first, all this cool information I gave you on those fan curves, it doesn't change how you read a fan curve depending on the technology you use, right? On the screen, I'm showing a bunch of different impellers. As long as the system has not changed, how the fan curve is read exactly the same. So that's kind of good. But the 2 most common types of impellers, wheels and props, I'll say it that way. Props, high volume, low CFM. My rule of thumb is 1 inch of pressure or less is ideal for a prop. Now, mind you, I've seen props that can do well over 2 inches of static pressure, but it's just not their sweet spot. Also, if you spin a prop, and you're pushing air through, you're kind of slapping that air. You're creating a high and low pressure scenario. Keep in mind that, like, if you're going against a lot of pressure, it's really easy for the air to wrap around the propeller blades, right? If there's pushback. And that's why they're not good at high static pressure. Now, when you pull in the centrifugal wheel, that pulls air in the middle and then it flings it out. It makes the air change 90 degrees. And it's hard for air to come back exactly the same 90 degrees. And that's why this is better at working against higher system resistances. And a lot of times you'll put a centrifugal wheel in a inline barrel or in a scroll, and that's going to make us change air twice at 90 degrees. And I think, yeah, here I show it. The top representation is an axial propeller, air goes straight through. The middle one, I'm showing that double 90 of that centrifugal wheel. That's why I can do a lot higher pressures because air can't find its way back. And then on the bottom, here's another type of technology that actually can affect efficiency, right? This is called a mixed flow wheel. And really it's kind of the love child of both a prop and a wheel. It takes the best of both worlds. And that's why my kids are good looking and really smart. Unfortunately, they got all that from their mom. But this is really taking that high flow capability of a prop and the pressure building capability of a wheel. But I'm only changing the air at 45 degrees versus 90, which takes less horsepower. So you're going to find more and more mixed flow wheels and everything from not just fan walls, but even square inline fans now are going to be employing this technology, which brings that fan in and it expands the size of the FEI bubble where it's greater than 1 because it is a more efficient and quieter impeller. So a couple of fan curves thrown on top of each other. That wheel, high static, lower CFM, that prop, the high flow, lower static, and kind of that mixed flow is that cross over all of it. So another one of your options are impeller types. All right, so we talked about kind of fan fundamentals. Reading a fan curve really is the start of everything for me. Worked into how that affects efficiency and some of your options, whether it's motor technology, fan type, fan size. But kind of want to circle back into fan curves here a little bit and look at, what happens when things don't go right. Right. So here's a scenario, and this is all under the system effect umbrella. Now, system effect is basically saying the inlet or the outlet condition do not match how it was tested, right? So I've got all this test data that's giving me this fan curve and all this information is great. But if you put a hard elbow at an inlet of a fan, the air is going to act differently. The efficiency of how the wheel grabs the air is going to change. The fan curve itself changes, right? So in our scenario here, this is exactly what we ordered. We ordered 1200 CFM at 2 inches. It was a beautiful curve. It was in a efficient point of operation in this fan's capabilities. Perfect. That's how I tested this fan. That's how I got all this data. And mind you, air moves into the fan beautifully smooth. It exits beautifully. Everything's gorgeous. But this is my installation we're going to have today, right? I have this fan where I am actually expanding and coming in at an angle. And then on the outlet, I'm restricting and at another angle. That does not look like how I tested this fan. And in this fan curve, let's kind of make it a little alive here, actually does not even look the same anymore. It looks completely different. And the point that I impact between my system resistance and my new fan curve is going to show quite a loss of CFM. Now, remember, fan curves offset parallel. If I speed that fan curve up, it maintains its shape, but I had to speed it up quite a bit. So in this scenario, I have a not opportune installation, right? I've created a scenario where the fan is less efficient at even moving air. And now to get to the right amount of right volume of air, I had to speed it up. So now it's going to be louder because I sped it up. It's going to be louder because it's in an inefficient zone, and it's going to be louder because the air is having to pull through. More air is going to pull through those same junctions. So I kind of wanted to get to this point where I showed you that, the best selection of a fan can be affected by final installation. I don't think that surprises anybody. But the surprise here comes at how much it can affect that fan's capability to move air. And I wanted to throw it all back onto a fan curve, which is where we started. All right, folks. I wanted to leave about 15 minutes for discussion, and it looks like we're right on schedule. That would be a first for me. John, are there questions within the chat that I can speak to?
Not yet, but it's a great reminder to everybody throw your questions in there. I had a thought as we were going through. You showed a lot of different fan curves earlier in the presentation, and I noticed that it looked like a lot of those were available. It looked like you were in sort of a desktop version of CAPS.
Absolutely.
And I was wondering, are these sort of standard fan curves that someone might encounter anywhere, or can they find them in ECAPs?
That's a great question. Let's kind of get back to here, right? My favorite fan curve. Within the full CAPS engineering version, you can see that there are tabs. I'm in the fan curves tab, and there are several curves across the top, right? Operating condition, that's that original fan curve we first looked at, CFM, static, and brake horsepower. That, just gives you that. And then you have your size comparison, RPM family, min max, static efficiency, and total efficiency. Now, these are the common curves you'll find within the CAPS system. Depending on the type of fan you have, it may or may not show both static and total tabs. You may only see one of them. Like in a square inline, you would only see a total efficiency curve. But these are kind of your standards. Now, within ECAPS, there is that drop down. You make a selection, pick a fan, go to customize, I believe is how it throws it up on the side, shows you the weights, the sizes, budget, sound, all that really good information for making good decisions. Under fan curves, it does have a drop down area, and that typically provides you either just the operating condition or the min max. Those are the two common fan curves for ECAPS.
Well, that's good that the engineers have access to at least the best fan curve.
And one nice thing about ECAPS is I can, create a scenario. I want a rooftop exhaust, and it'll at the CFM, it'll give me an entire list of 100 different fans that could do this. A couple of things about ECAPS. If you click on the column header, it's going to reorder what it's presenting to you, high to low and low to high, if you click it twice, by just that one criteria. So if you're doing a church or a theater, sound might be one of your overriding critical points. So, go over to decibels, A-weighted, and click on it, and now, show it from quietest to loudest, right? Or if I'm looking at efficiency, I have to meet these codes, or I'm trying to get, whatever benefit from a better fan selection, I can order it by FEI, fan energy index. So that is really good information there. Not to mention, you can pick up the 3 different fans and hit compare. And now you're comparing 3 fan curves, where they're at in each operation. Compare their cost, their sound, their size, all that using that compare function. Pretty useful
tool. Yeah, I remember using that when I was a designer, and I still use it now. We got a question in the chat from Brian. He's asking about the options for controlling EC motors and fans using EC motors, and what applications, an EC motor and a fan using an EC motor would be best suited for.
Great question. So when it comes to controlling EC motors, I can't say this is universal, but I know at least across our company, you have an option of a dial, which is a very simple and easy to use way of doing test and balance, right? I can just turn the dial to the right amount of airflow and leave it. I can turn power on and off, and away I go. But there's usually a 0 to 10 volt input. Now, when you use a modulating signal, and 0 to 10 is used for all kinds of stuff. I mean, I could be relaying information about parts per million, or position, or speed, using a modulating signal. And 0 to 10 is like the most common modulating signal in our industry. Secondary would be 4 to 20 milliamp. But 0 to 10, most EC motors can accept that. And it's a linear signal. So if I'm sending 5 volts, I'm telling the motor to go 50%, 10 volts, 100%. Now, what that does is that opens the world to controls, right? Now I have access to, anything less than 2 volts is going to be an off command. So now I have a start stop using just a 0 to 10 and the ability to set the speed. This really opens up what type of design philosophies I can employ, whether that's, different points of operation depending on criteria, whether that's, working off of a thermostat or a PID controlled thermostat that's going to modulate the speed of the fan to maintain a set point, right? There's a lot of different controls, and I guess the way I look at it, GreenHeck provides a pretty good selection of fan controls, very green controls as we would call them. But because I respond to a 0 to 10 volt signal, I can use controls from anybody that outputs a 0 to 10. I mean, that's great. Mine are, I've sized them and set them up for specific scenarios and tested them for function and all that. But they all use 0 to 10 as that carrier. And really that ties across to when I employ VFDs as well. Most every VFD I deal with accepts a 0 to 10 volt signal as well. So really the same controls can control EC motors, VFDs, right? So I'm kind of on the same platform. Now, when we kind of start tying this back into application, boy, there are so many different applications where this is beneficial. I could have a normal air movement for a stairwell, but then I have an alarm point where I'm maintaining 1.1 inch in a stairwell when there's a fire condition, right? Now I can just turn a fan on to a normal set low point, or if the fire alarm goes off, I have a constant pressure control, a differential pressure transducer, and I can modulate the airflow to maintain that 0.1. So that's just kind of an example of where an EC motor or VFD is very nice, right?
You mentioned the 10 volt signal being the 100% fan RPM. Would that be like the green line on this fan curve, or could that be something else?
So typically that would be the green line on this curve. That's what 10 represents.
But
now if I
it
put
could
a
be
bigger
programmed to be something else.
Yes, absolutely. So in this scenario, if I put an EC motor on this, and the 1 horsepower motor is going to run out of out of horsepower break at that 1530 point, I'll actually program in the ceiling for that motor's function, right? I'm going to program in 1530 fan RPM max. And then when you define a max point, that defines what 10 represents and scales from there. So it's very common actually, if you EC motor fans, right? You might find where I have a 1250 CFM, or excuse me, RPM, a 1250 RPM max condition. Now, it's not because the motor can only go 1250. It's because the manufacturer programmed it to stop at 1250 because that's where you run out of horsepower. The same motor in a smaller fan, it might allow 1725 RPM. Now that is represented by 10. So wherever your max programmed is represents full speed.
Got it. And that's a program from the factory, right? That needs to be known, at the time of ordering.
Yep. And if you look at your submittals, it's actually right on that kind of that first page. It'll say, my point of operation, use the one on the screen as an example, is 1448. My max is 1530. So we're telling you where the ceiling is, right on the submittal. And that, is again, that's a good point for, well, that's at 95%. I'm not comfortable, like me personally, now mind you, I'm spending your money. But me personally, I like picking fans at about 80 to 85%. I like a little more turn up to overcome that system effect, overcome a couple extra elbows that happen in every project. So that's me personally. That's my comfort zone is, 80 to 85%. So I would look at this selection and say, not quite. I'm going to bump the motor up from a 1 horse to a 2 horse. I'm going to buy myself a little more top end, and that's going to decrease the likelihood that I'm going to get a call back on installation day when they're bumping these and testing, and I'm short on air, right? I'm going to put a little extra in, but be warned, I'm now spending money to get to that comfort zone. So that's really, a lot of this is providing you guys the information to make good choices, or at least educated choices, right?
Yeah, that sounds like something that the designer and maybe somebody on my end or somebody on the ordering end, it'd be good to communicate. Maybe in SD's DD space, what kind of static estimation is this? So do you have a large safety factor in there? Do you expect it might be lower or higher? That could be an important conversation. No more questions in the chat, but I did have another thought. You said there was a dial on the fan signal. Can you combine some of these controls? Like, could you have a dial that you use to balance, and then the 0 to 10 is from maybe where the dial is set to off?
On most EC motors that I deal with, the plug-in is, you either plug in the dial and that's your function, or you unplug it and plug in a wiring harness. So you're going to use one or the other. But really, this opens up a controls, theory that I can employ. There are products like what I would call a Verigreen Handoff Auto, or HOA. A simple little box that gives me 2 points of operation, or it gives me the ability to put in hand mode and define the speed. And then I have an override speed. If a carbon monoxide alarm goes off, I have, a simple control that can give me that on off, set different speeds. So, the dial, I mean, if you know that you're only killing power and turning power on for this fan, and you just want to set at one point, it'll live there. A dial is a nice way to go. Anything more than that, like that HOA is an awesome little product. It acts like a remote dial. It acts like a 0 to 10. It does all these things, incorporates aux contact, so I can actually make and break power for your damper actuator. You start integrating or interlocking your systems together, which really reduces your installation time and the cost of all the different parts going into it.
The Handoff Auto has a great reputation.
Yeah, that's a problem solver for me.
Well, seeing no other questions in the chat, and we're just about at 1 o'clock. I'll let everybody go. Thanks a lot, Greg. That was great. I love seeing stuff about fan curves. And everybody, next week, same time, same day, we've got our presentation on DOAS, which is really popular. So looking forward to seeing everybody there. And thanks again, Greg.
Thank you for your time, folks. Have a wonderful day.